The sun captured our hearts with its bright beauty since the beginning of time. Our ancestors stared up into the sky, fascinated by its magnificence. Some thought of it as a god, for others a waystone to something greater. It's the center of our solar system, warming our rock in the vacuum of space and brightening our lives with its beauty and light. But what is light? Well, James Clerk Maxwell proposed light to be a transverse electromagnetic wave using his own famous equations. 22 years later, Heinrich Hertz experimented and produced radio waves using this device, therefore proving Maxwell's theory that light is in fact a wave. Photons, proposed by Einstein, are the particles of light, being discrete particles of energy that can be absorbed and reflected by matter. Electromagnetic radiation can actually behave as a particle and a wave. This is known as the wave-particle duality theory. This theory gets pretty complicated. I'm generalizing a little bit, but just bear with me while we go through this. In essence, a particle is localized, it has a definite location, whereas a wave is spread out. The electromagnetic spectrum displays the different wavelengths of moving photons. Adding waves of different wavelengths means that the resultant wave packet will be somewhat localized and there'll be less uncertainty about the location. However, what is the momentum of the object being represented by the resultant wave? Louis D. Dustu theorized a theory that states the momentum of a photon is equal to Planck's constant divided by the wavelength. This means if a wave has a precise wavelength, it has a precise momentum, but waves are infinitely long, and they're not at all localized. This relationship implies that there's a trade-off between knowing an object's position and knowing its momentum. This is known as Heisenberg's uncertainty principle. It's impossible to measure both the exact position of an object and its exact momentum at the same time. But stop. Let's go back. Back. The universe is such a big place, it's almost impossible to comprehend. The distance from the sun to our planet is 152 million kilometers. 1 light year is 9.5 trillion kilometers. The closest star to us, Proxima Centauri, is 4.2 of these. Light, seemingly the fastest thing in the universe, is incomparable to the distances of the universe. If the sun suddenly vanished, it would take over 8 minutes before us here on Earth found out. For Pluto, 4.5 hours. The light we can see is only a tiny portion of the universe. There's so many places we can barely imagine, so much matter and information that we're missing. We may be alone. Earth may be an anomaly. The exact sequence of events that led to us may be limited edition. We've had so many close calls with asteroids and other dangers that losing the game because of ourselves would be nothing short of a catastrophe. The Earth is getting hotter, dangerously hotter. That's no secret, but why is that? Well, let's go back to the electromagnetic spectrum. The wavelength of photons represents how much energy they carry. A shorter wavelength has more energy, while a longer has less energy. When photons are absorbed by molecules, the energy they carry can excite movements and vibrations in the electrons, transferring energy into thermal energy, or heat. Our sun emits solar radiation that consists of visible light, infrared radiation, and UV light, among some others. When this reaches our atmosphere, the sun's energy is absorbed by the land and the oceans, which heats the planet. Thanks to convection, this heat radiates outwards towards space. Greenhouse gases in the atmosphere trap some of this heat inside, keeping the Earth warm enough for liquid water to sustain life. Throughout history, this has been a careful balance, but now, with the extra greenhouse gases humans emit, there's too much heat being trapped, breaking the balance and causing adverse effects.